Okay, good morning, everyone, and welcome to Geoscience BC's webinar. I'm Gavin Durham, President and CEO of Geoscience BC. This webinar is in regards to our 2023 Scholarship Program recipients. So I'm speaking to you today from the city of Vancouver on the territories of the Musqueam, Squamish, and Tsleil-Waututh peoples. And I wish to acknowledge that Geoscience BC is publicly available and independent research takes place in the territories of many First Nations throughout British Columbia. Today, we're going to hear from 8 scholarship recipients: Lindsey Abdale, Behnaz Bahroudi, Kiera Broda, Joanna Dlugosz, Russell Johnston, Giovanni Pamparana, Kyle Powers, and Derek Shu. We would like to thank Lithos Geological Inc. for sponsoring this webinar, and also wish to thank Tech Resources for being a sponsor of the 2023 and 2024 scholarship programs. Just going to advance the slide here. This is Lithos' slide, and again, thank you very much for sponsoring this webinar. So for this webinar, we partnered with our friends at AME. Jonathan Buchanan, who's with us, is our Vice President of AME, will moderate the Q&A session. Note, this webinar is being recorded and will be available on our website soon. A little bit about Geoscience BC. So we're an independent, not-for-profit research society. We put out public research, which we believe informs evidence-based decisions by industry, First Nations, governments, and communities. It drives investment to British Columbia and is the first link in the supply chain for Canada's net zero emissions economy. I encourage you to think about how independent public geoscience can advance your project or technology and how you can contribute. To be successful, Geoscience BC model needs collaboration and for you to take action and either join Geoscience BC as a member, be part of the conversation about the type of research that is needed, fund or provide in-kind contributions to research and receive significant benefits, such as increasing your corporate profile, or, for example, gaining access, early and confidential access to research findings and data. And we need you to advocate for independent public geoscience because not everyone actually understands the important role that it can play in advancing critical minerals, energy, water, and carbon storage research. It enables opportunities, solutions, and attracts investment to the province. Now back to AME. The Association for Mineral Exploration was Geoscience BC's founding organization and a strong advocate for Geoscience BC now. A person who really gets it is AME's President and CEO, Kiera Broda, who will be joining us today or via Jonathan Buchanan to share a few words about AME. So thank you very much for everybody's support and look forward to hearing from the students. Thank you. Over to Jonathan.
Thank you very much, Gavin. Pleased to represent the Association for Mineral Exploration. I am Jonathan Buchanan, Senior Vice President and Chief Operating Officer of the organization. AME and its members have always valued public independent geoscience. Successful mineral explorers and developers depend on it, and this is why AME was a founder and proponent of Geoscience BC in 2005 and is a strong advocate today. Geoscience BC's research has proven to attract interest in BC mineral exploration. In fact, for every dollar invested in Geoscience BC minerals research to date, over $7 has been invested in mineral exploration and development throughout the province. So that's a return on investment of 7 times. Geoscience BC has been through significant and successful changes in recent years and has an important role to play in our future. To continue to succeed, it needs active support from industry and others. And our industry needs young talent, and we're very pleased to be part of today's webinar celebrating the research of 2023 Geoscience BC Scholarship Program recipients. So these are certainly some of the bright young minds that will lead us tomorrow. And we have several recipients today. And our first speaker is Lindsey Abdale, a PhD student at UBC. Lindsey is presenting on the Cotton Belt lead zinc deposit of southeastern BC, the world's first volcanogenic deposit associated with a carbonatite. Lindsey is a PhD candidate in geology with Professor Lee Grote at UBC. She received her BSc from the Earth Sciences Department at the University of Michigan, where she worked as a research scientist, she worked with structural geology professor Ben van der Ploem. Before pursuing a graduate degree, she worked as a research scientist with the U.S. Geological Survey in the Critical Commodities Group. Her current PhD research at UBC involves a complete physical, mineralogical, and geochemical characterization and understanding of a rare extrusive carbonatite in BC's southeast region. Based in Revelstoke, Lindsey also enjoys extensive heli-supported field work for this project. Beyond her thesis project, Lindsey is also interested in pursuing exploration geology. Please welcome Lindsey.
Hello. Can you see my screen all right? Okay, so I'll just...
Not quite yet. Perhaps, Gavin, you can stop sharing yours. There we go.
Okay, great. You can see it now. Can you see my screen now?
Yes, looks good.
Okay,
Go ahead,
great.
Lindsey.
I'll get started. Sorry. Okay, yeah, so I'm Lindsey. I'm 4 out of 5.5 years into my PhD, hopefully. And I'm presenting on part of my thesis research, testing the relationship between the Cotton Belt lead zinc deposit and the carbonatite cyanites in the Frenchman Cap Dome area of southeast British Columbia. So these are some field photos of the different types of carbonatites we have in the area. We have extrusive volcaniclastic Mount Grace carbonatites, and we have intrusive sill-like carbonatites, as well as the Cotton Belt lead zinc deposit. So this study analyzes the lead isotopic signatures of the Cotton Belt lead zinc deposit and the underlying carbonatites in order to test their genetic relationship, as well as address an age conundrum. So the geological setting is, like I mentioned, in southeast British Columbia near Revelstoke, and we're actually in an exhumed core complex that has brought up ancestral North American craton rocks and sediments. Stratigraphically, the Cotton Belt lead zinc layer is the highest, and it's underlain by about 100 meters by the extrusive Mount Grace carbonatites and by another 400 or 500 meters by the intrusive carbonatites in orange here. So the original deposit model for the SEDX lead zinc layer was for the Cotton Belt lead zinc layer was a SEDX. However, Trygg Hoy in 2002 noted a couple chemical and mineralogical differences, namely a magnetite host instead of pyrite, and some enrichments and incompatibles like calcium, manganese, fluorine, phosphorus, and rare earths, and reclassified Cotton Belt as a broken hill type deposit. So the current model assumes oxidized sediments and low temperature, high salinity reducing fluids that lead to an alkali-enriched metal zone. Carbonatites, for those of you who don't know, are igneous rocks with greater than 50 volume% carbonate minerals. They are most commonly intrusive, like we saw in my field site with the Wren carbonatite, but they are sometimes extrusive as well, like we saw with the Mount Grace carbonatites. They're thought to be sourced from fairly deep in the mantle. They represent really, really low degree partial melts of a carbonated mantle peridotite. So that enriches them heavily in these incompatibles, namely rare earth. They're the leading ore deposit for rare earths, high field strength elements, fluorine, phosphorus, and manganese. So something I noted is the similarities in chemistry and incompatible element enrichment between carbonatites by nature and the Cotton Belt lead zinc deposit. So that led me to my first research objective, which was to test the genetic relationship between the lead zinc deposit and the underlying carbonatites. So the Mount Grace extrusive carbonatite and some of the intrusive carbonatites in the area have zircon, uranium, thorium, lead ages of 360 million years. The overlying carbonatite lead zinc layer has a lead model age of 580 million years. And I'll get to this method in the next slide. So that led me to my second research objective, which was to address the age conundrum between an older overlying lead zinc deposit and the younger underlying carbonatites. To do that, I'm going to test the validity of the cotton belt lead model age itself. So how these model ages work are based on these lead growth curves from the beginning of with bulk earth composition initial lead isotopic ratios at formation. And they're an empirical fit line between the lead isotopic composition of stratiform deposits and other sediments. The shale curve being specific to the Cordilleran sediments. And what you can do is you can plot isotopic ratios of unknown ages of deposits on the shale curve and get a model age. So the shale curve model age for cotton belt is only applicable if the lead of cotton belt came directly from the host sediments. Whereas if the lead was sourced from a magmatic rock, then the shale curve would not be applicable to date the cotton belt. So that leads me to my methods for this study, which is the lead isotope analyses via multi-collector ICP-MS of the cotton belt and the regional carbonatites to see if there's any overlap or mixing in the data that would indicate a genetic relationship and test that age conundrum. So the results of my data I've plotted as stars in a couple lead-lead plots. The lead isotopes of cotton belt are shown in red stars, and those of the regional carbonatites in blue and purple. And you'll see that they don't overlap, so this doesn't prove any sort of genetic relationship or really address the age conundrum, unfortunately. However, we did notice that they form a linear trend, and that this linear trend is similar to this Cordilleran carbonate trend that was first noted by Nelson et al. 2002. The idea behind this is that the ancestral North American western margin in the Devonian Mississippian experienced low temperature, low pH hydrothermal circulation in the back arc that led to a lot of the ore deposits that we have that are Devonian Mississippian in age in the Cordilleras. And the idea being that those hydrothermal fluids leached radiogenic lead progressively from west to east and created this linear future plotting radiogenic lead of carbonate sediments and deposits. So my current hypothesis is that the carbonatites with those zircon late Devonian age populations likely experienced a similar hydrothermal alteration event. The fact that my data forms this similar linear trend might also indicate that the cotton belt was that the hydrothermal event led to mineralization at the cotton belt deposit, but I'm still testing that hypothesis. So that's about it so far. I have some new zircon geochron work that I'm going to be looking at to validate that 360 carbonatite age. And these are my references. So if there's time for questions, I'll take them.
Thank you very much, Lindsey, for the presentation. Certainly feel free to enter any questions in the chat. And my first question, Lindsey, is given your experience with the USGS, are there similar deposits elsewhere that these compare to, or is this something new and unusual for you?
Yeah, different for me. There are not any known lead zinc deposits lead zinc deposits associated with carbonatites in the literature. There's a couple in Alaska that are associated with other alkaline rocks. But this would have been a first if they are somehow related.
Wonderful. And anywhere in particular that you're looking to get out to in the field?
I've done a lot of field work already, so hopefully not too much more. These are relatively accessible, but they're all all the carbonatites and lead zinc deposits in the core domes that I've been looking at are all relatively accessible and close to each other. So I don't need too much more field work for that, but some sort of stratigraphic unconformity or something like that would be another idea to test the age conundrum. So if there was opportunity for like some more detailed structural and stratigraphic work, that would be useful.
And we do have a question from Lucia. Have you observed the two units together in the field?
Yeah, so they're probably about 100 meters apart in the field. They're both at this point kind of stratiform lenses, so they're along stratigraphy. But yes, I have seen the both of them in the field.
Perfect. Yeah, thank you very much, Lindsey, for your presentation. Our next presenter is Behnaz Bahroudi. Behnaz is an MSc student in environmental science at Thompson Rivers University, specializing in mine reclamation practices under the supervision of Dr. Lachlan Fraser. With a BSc in civil engineering from Iran, Behnaz joined Dr. Fraser's lab to conduct research on the reclamation of closed tailings storage facilities at New Afton Mine near Kamloops in BC South Central region. Her research focuses on determining appropriate soil cover depths and amendments to restore sustainable ecosystems in tailings storage facilities. Presentations at symposiums and conferences, some of which I've had the pleasure to attend, allow Behnaz to share her findings and raise awareness of the project. With a passion for effective mine closure and reclamation, Behnaz aspires to make positive impacts on local communities as she continues her career in this field. Behnaz is presenting on topsoil till cover, depth and amendments, influence on ecosystem reclamation in closed tailings storage facilities. Please welcome Behnaz.
Thank you so much, Jonathan. Can you see my screen right now?
Looks perfect.
Okay, great. So hi, everyone. I'm Behnaz, and I'm studying the influence of topsoil till cover depths and amendments on ecosystem reclamation of the closed tailings storage facility. So my research involves a greenhouse study at Thompson Rivers University, and also a field and a lysimeter experiment at New Afton Mine. But today I'll be sharing the findings of the greenhouse study. As you know, mining and extraction of minerals and resources have been central to human development, driving industries and economies, while supplying materials for renewable energy technologies. However, there is environmental risk in the extraction of natural resources. Mining activities can change the land ecology and affect the environment through loss of native vegetation, reduction in biodiversity, and introduction of invasive species that ultimately decrease the terrestrial ecosystem's quality. Tailings, one type of mine waste material, is produced during the processing of minerals. And this material can contain heavy metals and are required to be deposited in tailings storage facilities, or TSF. The construction of TSF involves the removal of topsoil, subsoil, and material from land that can be expanded by several kilometers and reach tens of meters in depth. And the environmental risk involved with TSF can be mitigated if the disturbed land is effectively managed and properly reclaimed. Okay, so to reduce the environmental effect of mine tailings and promote ecosystem development, placing topsoil and subsoil cover depths on top of tailings has become a common and direct way of reclamation. The topsoil and subsoil that were removed before the construction of TSF can be reapplied and re-leveled to provide planting medium. However, the disturbed topsoil and subsoil may not be as nutrient-rich as they were before the removal due to stripping, long-time stockpiling, and reinstatement. Therefore, it is important to incorporate appropriate amendments that can help with soil structure and also improve microbial community and enrich soil with organic material and carbon sources to reactivate nutrient cycle. So this study delves into the utilization of zeolite, a crystalline aluminosilicate derived from volcanic rocks, and leonardite, a naturally occurring form of oxidized lignite abundant in humic and fulvic acids. And lastly, a fortified compost made of wood waste, urea, and a mixture of composting microbes. This research is conducted to examine the influence of mentioned amendments individually and in their combination on the growth of blue bunch wheatgrass and soil properties when covering tailings. For this study, tailings were collected from New Afton mine, exactly from the historic Afton tailings storage facility located at New Afton mine, approximately 10 kilometers west of Kamloops in British Columbia. So in the greenhouse study, the pots were filled with tailings and then covered with 20 centimeter of subsoil and 10 centimeter of topsoil that were collected from New Afton mine stockpile. Then zeolite, leonardite, and a combination of zeolite and leonardite were mixed into the topsoil in 2 different ratios. And furthermore, the effect of incorporating 10 centimeter compost covering topsoil was examined. So therefore, we had 14 treatments replicated 6 times for a total of 84 pods, and each pod were seeded with blue bunch wheatgrass seeds. So at the end of the experiment, soil, root, and shoot samples were collected, and they were analyzed using R software, primarily with lineal models, to demonstrate the result that I'm presenting today. So moving to the result, the left figures show that compost addition significantly increased total soil carbon and nitrogen content. And in the right figure, we can see that compared to leonardite treatments, zeolite resulted in significantly higher total nitrogen level. It also shows a greater increase in total carbon content compared to both leonardite and the combination of zeolite and leonardite as amendment. In terms of soil organic matter, also we can see a similar pattern to total nitrogen. There is also a significant difference in total biomass between treatments with compost and the ones without. However, the addition of leonardite, zeolite, and their combination did not show a significant influence. Analyzing the root to shoot ratio, we can see in the left figure that compost amended treatment led to a value less than 1. This corresponds with the right figure, which shows higher shoot growth in compost amended treatments compared to the control ones. And these findings can suggest that there is an abundance of nutrient in the compost amended treatments that leading to an increase in above ground biomass production. So in conclusion, compost amended treatments significantly increase soil organic matter, total carbon, total nitrogen, and biomass compared to unamended treatments. Zeolite treatment also led to significant increases in those elements compared to leonardite treatments. And compost addition resulted in a root to shoot ratio below 1, an increase in shoot biomass, and finally, no significant influence of different amendment ratios were observed. In my next step, I'll be working on ICP-MS analysis of soil and plant samples to assess the effectiveness of zeolite, leonardite, and compost in eliminating potential trace elements, which can provide a more comprehensive understanding of these amendments. And I think for future research, it would be great to see the long-term effect of zeolite and leonardite in higher ratios, hopefully in field sites, to gain more detailed understanding of these sustainable amendments. At the end, I would like to thank all the sponsors of this research, and a special thank you to Geoscience BC for the scholarship and the opportunity to present my research. And I take, if there is any question, I would be happy to answer.
Thank you very much, Behnaz. As always, please feel free to enter your questions in the chat. One question I have is based on the properties of leonardite and zeolite, did you anticipate the observed results on plant growth and soil properties?
Yeah, so before starting the research based on the previous studies on these amendments, I was expecting to see a great biomass growth with zeolite, but I was so excited to see the influence of both zeolite and leonardite together. Unfortunately, I didn't see that in my study, but that might be because of the number of replication in the greenhouse study. If I could have more replication, I might be able to see this. So that's why I recommend more field studies with different ratios and more replications.
It'll be great to see how that turns out. And is increased shoot biomass compared to root biomass in compost amended treatments a positive or negative outcome, and why?
Yeah, actually, this was really interesting when I saw this result in my research, because this root to shoot biomass can show kind of like how plant prioritize like the root or shoot growth. So based on literatures, when there is abundance of nutrient in soil, plant prioritize shoot and production over root increase in soil. But when there is low nutrient and plant is under stress, there are going to be more root growth to kind of like go deep and kind of like reach to those nutrients. So yeah, I think it's a positive outcome, and it shows that compost did a good job in providing nutrient for the soil.
Yeah, thanks very much, Behnaz. Our next presenter is Kiera Broda. Kiera is presenting on controls on the nickel mineralization of the early Jurassic Alaskan type ultramafic in the Turnagain complex. Kiera is a PhD candidate in the Department of Earth and Planetary Sciences at McGill University under the supervision of Dr. Anthony Williams-Jones. Since 2014, Kiera has worked on several ultramafic nickel sulfide projects, including the Nickel Shaw deposit and most recently the Turnagain deposit. Kiera's passion for geology began in childhood during vacations through the mountain ranges of the Canadian Cordillera, and this early passion transitioned to an academic focus in 2012 upon joining a bachelor program in geoscience at Vancouver Island University. Please welcome Kiera. Yep.
Can you hear me now?
Yep, screen looks good and I can hear you well.
Oh, sorry, I was still muted there for some reason. Thank you all for attending the Geoscience BC webinar today. Today, I'll be giving you an overview of my research, which is focused on understanding the controls on nickel cobalt mineralization in the early Jurassic Alaskan type Turnagain complex. Sorry about that. Can you guys hear me now and can you see my screen?
Oh, no, yep, this looks good now. And
Okay, sorry. For some reason, I was on mute and then my slides were switching on me. So anyways, okay, so Turnagain is an unusual example of an Alaskan type complex in that it hosts significant nickel cobalt sulfide mineralization. Magmatic processes have generally been invoked to explain the mineralization. However, there's often significant overprinting by post-magmatic modification processes. So the goal of my research is to evaluate the role and relative importance of magmatic and post-magmatic processes in the genesis of nickel cobalt mineralization. So Alaskan type complexes are a distinct class of ultramafic to mafic igneous complexes formed through the emplacement and fractional crystallization of a hydrous magnesium-rich basaltic magma. These magmas are derived from fluid-induced partial melting of the mantle wedge at convergent plate margins. They are composed of olivine, clinopyroxene, and hornblende, and distinctly lack orthopyroxene. The presence of hydrous minerals like hornblende, the absence of orthopyroxene and their plate tectonic setting set them apart from other ultramafic intrusions and complexes. Because of their relatively oxidized nature and depth of formation, they typically are undersaturated with respect to sulfide and do not host significant sulfide mineralization. So Turnagain is located in northern British Columbia, approximately 70 kilometers east of the town of Dease Lake, and it's part of a 250-kilometer long belt of Jurassic-aged Alaskan-type complexes that extend from Turnagain in the north to Polaris in the south. It is hosted in metasedimentary and metavolcanic rocks with possible Yukon-Tanana or Cornelia terrain affinity. The Turnagain complex has been divided into 4 zones, with each zone representing a separate intrusive body. Zone 1 in the northwest part of the complex consists of wurlite and olivine clinoproxenite. Zone 2, which hosts the Turnagain deposit and is the largest intrusive zone, is composed of dunite, wurlite, and olivine clinoproxenite. Zone 3 is a small diorite lens that occurs in the center of the complex, and it intrudes part of Zone 2. Finally, Zone 4 is composed of clinoproxenite and hornblendite that intruded Zone 3 to the north and Zone 2 to the east. The entire complex intruded and is hosted by middle to late Paleozoic graphitic phyllite and metasedimentary volcanic rocks. The southern contact is an intrusive contact. However, the rest of the complex is in fault contact with graphitic phyllite and is separated by a basal thrust fault. Wall rock enclaves occur in most units. However, they're more numerous along the southern intrusive contact. My area of focus will be in the southern part of Zone 2, where the Turnagain nickel cobalt resource is located. So the study area is characterized by interfingered dunite, wurlite, and olivine clinoproxenite. The nickel cobalt sulfide mineralization, which occurs as assemblages of pyrrhotite and pentlandite, is scattered throughout the study area, but it tends to increase proximal to the wall rock enclaves and the wall rock contact. The assimilation of sulfur and graphite from these wall rocks is thought to be the reason for the formation of magmatic sulfide. Additionally, there is variable but significant overprinting of primary textures by post-magmatic processes. So in order to understand the genesis of the nickel cobalt mineralization, I need to characterize both the primary and secondary processes affecting the deposit. To do this, I will start by examining the textures and chemistry of olivine and pentlandite. So primary olivine is characterized by cumulate, subhedral to euhedral grains that occur with increasing portions of interstitial clinopyroxene as lithologies progress from dunite towards clinoproxenite. Primary olivine is often overprinted by 2 post-magmatic textures, the first one being the replacement of olivine by serpentine minerals during the process of serpentinization, which is essentially the hydration of olivine, and the second being the formation of olivine pseudomorphs that form by the dehydration of serpentine during tectonic decompression. In the image on the right, we see that this beautiful texture here where at time 1, serpentine nearly perfectly pseudomorphed an olivine crystal, and then at time 2, during dehydration, a secondary olivine crystallized along the edges. These 2 processes are important because during serpentinization, the magnesium leaves the olivine and forms serpentine, whereas any iron in the olivine is released to form magnetite, and any metals like nickel and cobalt in olivine are released to form sulfides. So these 2 olivine textures have very different chemical signatures. So electron microprobe analysis shows that primary olivine has lower magnesium numbers and generally lower manganese oxide than secondary olivine. The negative correlation between magnesium number and manganese concentration in primary olivine is consistent with crystal fractionation and falls within range of typical convergent margin olivines, whereas the elevated manganese in secondary olivine is inferred to result from the presence of manganese-rich fluids formed during dehydration. Also, primary olivine generally contains more nickel than secondary olivine. Nickel concentrations in primary olivine are consistent with crystal fractionation from the silicate melt, either in the presence or absence of a sulfide liquid, while the low nickel concentrations in the secondary olivine correlate with the formation of olivine from nickel-depleted serpentine during dehydration. With respect to sulfide mineralogy, we also see primary and secondary sulfide textures. So the primary sulfide textures are characterized by interstitial disseminated to net textured assemblages of pyrrhotite and pentlandite that vary in portion from nearly 100% pyrrhotite to 100% pentlandite. Within the sulfide assemblages, pentlandite commonly occurs as large blocky grains and rarely occurs as exsolution flames in pyrrhotite. In addition to the primary textures, we also see secondary textures represented by cross-cutting veins of pyrrhotite, pentlandite, magnetite, and serpentine, or by sulfide pseudomorphs of olivine and serpentine as seen on the right. The association of serpentine with sulfide mineralization indicates that significant remobilization of sulfur occurred at the same time as serpentinization. The primary pentlandite is characterized by lower cobalt content and a wider range of nickel-iron atomic ratios than the secondary pentlandite. Primary pentlandite compositions are likely to be controlled by temperature of crystallization. At high temperatures above 600 degrees, the nickel-rich pentlandite may crystallize in equilibrium with sulfide melt or monosulfide solid solution, whereas temperatures below 600 degrees, pentlandite forms by exsolution from pyrrhotite, resulting in lower nickel content pentlandite. High cobalt concentrations in secondary pentlandite are thought to result from the release of cobalt during the serpentinization of olivine and sulfides. Cobalt is remobilized into sulfide and substitutes for iron and nickel in the pentlandite structure, resulting in higher cobalt concentrations in the secondary pentlandite. So to summarize, Turnagain is a unique example of an Alaskan type complex that has significant sulfide mineralization and exhibits a mix of primary magmatic textures and overprinting secondary textures. Post-magmatic processes result in textural and chemical changes that are important to understand in order to evaluate the role and importance of magmatic and post-magmatic processes in forming the nickel cobalt sulfide mineralization in the Turnagain complex. Thank you.
Thank you very much, Kiera. One question, you mentioned that Turnagain is unique, that it has sulfide mineralization. Why do most of Alaska types not have sulfide mineralization?
Typically, when the magmas form at the mantle wedge, they're undersaturated with respect to sulfur. So being that they start off undersaturated, as they're emplaced into the crust, the relationship between sulfur saturation and pressure is negatively correlated. So you move up through the crust, you decrease pressure, you increase the solubility of sulfur in the magma. Therefore, by the time these magmas make it up into the crust, they are significantly undersaturated with respect to sulfur, and they don't form a sulfide liquid.
Yeah, thanks very much, Kiera. Another question, what is the relationship of the native copper at Turnagain?
Native copper, there's not really any native copper.
Okay, so thanks very much, Kiera, and we'll also have a Q&A session at the end, so if there are any other questions that come up, we can take them then as well. So thank you very much, Kiera. Our next presenter is Joanna Dlugosz. Joanna completed her BSc Honors in Geology at the University of Calgary in 2020. Her undergraduate thesis with Dr. William Matthews utilized laser ablation, inductively coupled plasma mass spectrometry, depth profiling of zircons to determine the stratigraphic age and provenance of the Leech River schist on BC's Vancouver Island. She is currently an MSc student at the University of BC Okanagan campus with Dr. Kyle Larson. She is collaborating on her research with Dr. Christopher Lawley from the Geological Survey of Canada and also Enduro Metals Corp. The research is focusing on the critical mineral potential and vectoring in the Burgundy Ridge copper gold porphyry deposit in BC's northwest region through sulfur isotopes and sulfide trace element maps. Please welcome Joanna.
Hello. Is that, oh, what? Sorry, hold up. I think I need to share a different screen and show, share and send. Does
It's on your the slide show preview mode still.
Oh, it is. Oh, it's still on the preview mode? That is Is it showing the title page now?
It is, but it's grayed out.
Or is it still doing the PowerPoint preview? Okay, that is interesting. Sorry, that was working earlier. Maybe if I... Okay. Stop share. Share screen. Let's go this one.
Yeah, it certainly was working nicely
Right
earlier.
now?
Not yet.
Okay. I'm not sure why it's doing that.
Okay, probably let's jump to Russell then, and we can come back after to you, Joanna.
Okay.
If Russell
Okay,
is ready,
sorry
if you don't
about
mind, we'll
that.
start to jump into it. It's our live, so.
Yeah, it's so weird. It was working when we checked earlier. I'm not sure what it's doing now.
Okay. Yeah, we'll try again in a few minutes.
Okay.
Our next presenter is Russell Johnston. Russell is an MSc student at the University of British Columbia. He grew up in Northeastern Ontario and completed his undergraduate studies in earth sciences at Carleton University in 2019. From 2019 to 2022, Russell worked as an exploration geologist across Canada, the United States, and Greenland, exploring for a variety of base and precious metals. During this time, he gained an appreciation for the importance of rigorous data collection and exploration. Russell is keenly interested in methods of integrating traditional field geology with modern exploration techniques to increase the success of exploration program. His MSc project focuses on unraveling the structural controls and tectonic history of the Galore Creek porphyry deposit in BC's Northwest region. Please welcome Russell. Yeah, that looks good.
All right, you guys can hear me and see me?
Perfect.
All right. Yeah, so I'm Russell Johnston. I'm rapidly approaching the end of my MSc here. Thank you for the introduction. As I think was mentioned, most of my research is on structural geology, but today I'm just going to give a quick rundown of the stratigraphy at Galore Creek, and some of the interesting things that we see there because it's quite a unique sort of deposit. And special thanks, of course, to Galore Creek Mining Corporation, the British Columbia Geological Survey, and of course, Geoscience BC for their generous support. So for those of you who aren't familiar, Galore Creek is a large copper porphyry deposit located in northwestern British Columbia. If you look at the Cordillera here, it sits in the Golden Triangle, which is sort of a colloquial term for this region here, hosted in the Stikine assemblage. The Stikinia. Stikinia is composed of three groups: the Stikine assemblage at the bottom, the Stuhini group, and overlain by the Hazelton group, which are the blue, orange, and purple on this map. And Galore Creek sits right at the very top of the Stuhini group. And it's very unique because it is extremely alkalic. It's the world's most alkalic porphyry deposit. So it has silica saturated to undersaturated intrusive phases and associated volcanic stratigraphy. And it's considered the global end member of alkalic porphyry deposits. So definitely interesting from that perspective. This is a map of the area that is a compilation of my work, as well as the work of Jim Logan, Esther Borte, and Gail Febo. And sort of the age of these intrusive rocks, which is sort of highlighted by these red zones here, is between 210 and 208 million years. They cut their own volcanic piles, so they were in place fairly close to surface. And the deposit itself is composed of many of these small mineralized centers, each of these blue squares here. And most of my research is focused on these sort of corridors that a lot of strain has been dumped into. So outside of them, rocks are not typically foliated, but within them you can have very, very intense zones of strain. And in particular, we're going to be focusing on this large one right beside the deposit with all of these interesting colors on the geologic map. So this one is called the Ridgeline Deformation Corridor. In the red here, we have very intensely altered, locally mineralized rocks. And on the west, we have rocks that are not mineralized, not altered in any way, but quite deformed. And I'm just going to run through the stratigraphy that we see here. So the interesting stratigraphy, or the unique stratigraphy, is all at the top. And the bottom here, we have a lot of conglomerates, sedimentary rocks, sandstone, siltstones, and of course, augite-bearing mafic volcanic rocks. If any of you have worked in Stuhini group before or are familiar with it, this will sound very common. These sorts of rocks at the bottom of the strat column are found for, hundreds of kilometers in all directions. And that sort of sits up in this area here. And then as we sort of get higher up in the stratigraphic sequence, we get into things like orthoclase spheric volcanic rocks, pseudo-analcime bearing volcanic rocks, and pseudo-lucite bearing volcanic rocks. So really weird, really uncommon, and part of the reason why Galore Creek is so interesting to so many people. I'm just going to quickly run through the units. So the lower calc-alkaline assemblage, as I said before, if you've worked in the area, you will be very familiar with this. Volcanic clast-bearing conglomerates, siltstones, augite, ferric, mafic volcanic rocks. Chemically, these are sort of identical to the Stuhini group regionally. So I wouldn't call them uninteresting, but they're certainly kind of generic. As we get a little higher up, we get into orthoclase-bearing volcanic rocks, and you can see in thin section here, absolutely beautiful. So we're sort of starting to get into the potassic facies, or the potassic phases of volcanism. For a long time, Galore Creek had always been described as being very potassic, but some of the work that we've done here has actually shown that there is a strong sodic component to a lot of this volcanism. And this is pseudo-analcime, which is a term that I made up for albite after analcime pseudomorphs. So you can see here in this really nice field shot, all these little sort of soccer ball shapes. And in thin section, we actually see that they're completely pseudomorphed, and they're all albite after analcime. And they're very interesting. They behave as rigid bodies, which is to be expected because albite is quite strong. And what's interesting from a chemical perspective is how sodic this unit is, because Galore Creek has always been described as very potassic, but we see that there is at least some component of primary sodic volcanism. And on top of that, we have what we call the coarse feldspathoid bearing volcanic unit. I usually just call it the pseudo-lucite bearing volcanic unit, but it actually consists of both analcime and pseudo-lucite. And the reason for that is that lucite as a primary phase is extremely unstable, and it typically breaks down in the melt into something called pseudo-lucite, which is an intergrowth of orthoclase and nepheline, and then from there it will break down into white mica and orthoclase. And you can see in this thin section here, beautiful zonation between sort of white mica dominated zones and orthoclase dominated zones. On the other hand, if lucite doesn't break down in the magma chamber and makes it to surface, it doesn't have a much better fate. It almost immediately will break down into analcime by alteration with surface water. This happens typically within a few million years. It's very rare to have lucite preserved for very long on surface, and we end up with analcime, which is what you see up here. So you can end up from one sort of composition of magma, end up with two very similar rocks that have the same origin. So these are the sort of rocks that we're dealing with in the area. And if you're working in the area or you're looking for an analog, these are some things to keep in mind, is that you're looking for not just normal alkalic porphyry deposits, but like really alkalic rocks that we sort of need to find this kind of deposit. And the whole rock geochemistry is not, I don't want to say not particularly interesting, but it plots exactly as you would expect. The sort of mafic volcanic rocks, the augite ferric rocks, plot mostly as basalts and trachybasalts, creeping up between the orthoclase bearing rocks and the pseudo-analcime bearing rocks into the phonotephrite field. And then finally, the pseudo-lucite bearing rocks plot mostly as tephrophonolites. So nothing particularly new, I would say, but definitely very interesting. I think it is interesting to note that there is a strong primary sodic component that's gone unrecognized in a lot of previous work. I'm not a geochemist, but certainly that's something to keep in mind if you're interested in that sort of thing. And then I just wanted to sort of summarize with some implications on regional exploration. If you're, say, for example, a VPX of a junior mining company with property in the area, this might be of interest to you. So Galore Creek formed near surface in the very last gasp of the Stuhini group volcanism, while uplift and erosion was ongoing. At the end of the Stuhini group, when the Stuhini group volcanism terminated, there was major uplift because Stuhini was colliding with the Yukon Tanana. So it's not just that you have to find an area where one of these deposits existed. You also have to find an area where it would have been preserved. So it makes it very tricky. And there are sort of two main ways that mechanisms we've come up with that it could have been preserved. One is either burial in a local extensional basin, and two is burial under thrust sheets. I've included this absolutely gorgeous thrust fault here. I think this is really fantastic. Galore Creek is just sort of peppered with these things all over the place. So you're looking for ways that you could have gotten this deposit away from surface as quickly as possible. And if you are sort of, in the market to explore for these things, you have to really consider that there's a very strong likelihood that they are buried under Hazelton strata. Yeah, and that's all.
Thanks very much, Russell. Is there any evidence that extensional basins played a role in controlling the emplacement of Galore Creek?
That's a really great question. So there's really good evidence elsewhere in the Golden Triangle, like KSM and the Big Bulk deposit. Some of my lab mates have done some work on that. We don't necessarily see evidence for it at Galore Creek. I didn't map any really obvious early growth faults or extensional faults in the field, but I think it's a very real possibility. And it's one of those things maybe there are, and the faults are in the valley. So it's unclear, but definitely a possibility, I would say.
Thanks. And yeah, I see there's another question in the Q&A. Perhaps we can get to that later, or if you want to type an answer, Russell, feel free. So thank you very much, Russell, for your presentation. Our next presenter is Giovanni Pamparana. He is a PhD student in mining engineering at the University of British Columbia. His research area is mining processing with a particular focus on comminution. His current work investigates compression comminution technologies and builds on previous research that combine modeling and laboratory testing in the areas of energy consumption, renewable energy integration, and ore breakage. He completed his undergraduate degree in mining engineering and his MSc in mineral processing and extractive metallurgy at the University of Chile. His project is a study on compression breakage from theory to practice. Please welcome Giovanni. Yeah, the screen looks good.
Perfect. Hi, everyone. Thank you for the introduction, Jonathan. This presentation, I want to show a very quick extract of my whole research that has different arms, basically. Is looking into how we can actually know the full characterization of the compression comminution in the ore. And this way we can impulse forward these newer technologies of comminution, rock breakage, so that we can actually promote the energy savings around the world. From one side, I've been looking into different things in my PhD. One is to know the theory of compression comminution, and the other one is how we apply this theory into the practice, how we can actually use it to take advantage and improve the modeling of this, basically a compression comminution, and use the main equipment that is being promoted for this, that is the high pressure grinding rolls, or HPR, short. So first of all, I want to make a quick introduction to what is compression comminution and what is the piston press test that is actually the test that I'm going to be using to model the HPR behavior. And I'm going to tell you why I'm doing this. As well, I'm going to show what is the HPR, how the size reduction and then consumption models work, and how is finally the throughput model that is the final stone into the whole modeling package of the HPR. So first of all, what is compression comminution? As the name says, we're basically breaking the rocks in by compressing them. So usually in mining, we're very used to tumbling mills that actually impact the rock and impact the rock with these grinding media, some big steel balls, iron balls, and they will break the rock. On another side, we also have attrition going, that is the rock and the balls like rubbing themselves. This way we're achieving comminution, but it is very energy intensive. So this is the reason why compression comminution is actually very useful, because it's way more energy efficient and allows to have the same breakage or even a better breakage than the classic ways that we have been doing. As well, it is giving a uniform particle size distribution that can be way more controlled for fracturing and allows for some downstream benefits, such as reducing the ore strength. So we use less energy downstream when we need to break the rock even more. So this basically, as the pressure we are exerting on the rock, we are generating cracks, they break, and also they will propagate, giving us this advantage. So this is the HPR technology. This is the pilot scale test machine that we have at UBC. And we use this machine to do several studies, and basically we can use it to size full-scale industrial HPR. How this works? Basically, we have these two rolls that will actually move, and we'll grind the material through them. We'll crush the material through them as it flows, and it gets feed from the top and basically gets grabbed and compressed. It's very, very simple idea, but it allows the material to be to break the material way more efficiently. So this HPR basically works by having two rolls pulling towards them, and the rock will generate a counterforce that will open the rolls. The one of them is a floating roll that is actually the one pressing, and the other one is being kept stable. Why is important to know this? Because the piston press, that is the machine that we're going to use to dimension this huge machine, uses the same principles. So basically, coming back a bit to summarize on the HPR, we have the different operational benefits. That is a high throughput that is very important for the mines. We need to have, they need to process a lot, especially nowadays that the grades are going down and they have to increase the volumes. As well, the size reduction is very good with very good recirculation load, and will have an improved metallurgical response. So it's a very energy efficient technology, but we need a lot of material to size it. That is why we use the piston press test. This lab scale test actually will simulate the HPR conditions. As I said, one roll pressing the other. This will be a piston pressing over the rock and in the same uniaxial direction. So compared to the HPR, we need usually more than 1 ton of material to make a sizing. In this case, we can use 500 grams to 600 grams, so we can have a full characterization with only 10 kilograms of material. That is huge for new projects. As well, we use basically this highly instrumented machine that will record the force displacement of the material, and we can know how it is breaking. And using this force displacement curve and the final breakage of the material, we can use it to model the HPR behavior with a certain degree of accuracy. And we can get finally the size reduction of the material on how it will behave in the HPR, the energy consumption, and the throughput. How this works? Pretty easy. We have there a piston and a die. So basically, we put the material inside the die, as we can see here. We put the material in the die, we put the piston on top, compress it. So we have basically this material after compression, and then we take it out from the die and we perform a particle size distribution analysis. And with that information, plus the force displacement curve that we get from the piston press, we can get the energy that we're using, the specific energy that is needed to break this material on the piston press test. And then by using this information, then using this information, we can actually use it to perform several models. So the first model I'm gonna go quickly through this is one developed by Damenyan in 2015, and he developed the energy size reduction models through different methodologies. The most important one is the direct calibration methodology that will allow us to see how the piston press energy compares to the HPR energy. As you can see here, this is the way we do it. Basically, we to a net specific energy, we can see how much pressure is equivalent on the HPR and on the piston press. And that comparison is basically allowing us to calibrate the behavior of the material in the piston press with the HPR. So how do we do this? Usually we do different runs on the HPR, and we can then do different runs on the piston press, and we can calibrate for a certain material. Afterwards, with this calibration will allow us to get the energy size reduction of the equipment for that material. The throughput model on the other side is basically giving us what would be the throughput, and this is my outcomes of this study is basically giving us how the direct calibration, using the direct calibration methodology, or by using a database methodology, because we have an extensive database in our hands at UBC, we can get basically a throughput, and this is how basically it works. We calibrate the specific energy with the force, and then we calibrate the specific energy with a certain displacement that will give us basically the throughput using a multilinear model. This is a quick result. So the specific energy modeling with a direct calibration will give a very good fit of the data. If we want to model the specific energy as well, it gives also a good fit, and we're talking about 25% error when we use the database. As well, for the size reduction, we expect a 10% error when we direct calibrate and a 25% error when we use the database. In my case, for the throughput, I'm getting a very good fit for the prediction, getting errors under 2% of prediction, and this was using several ores from different deposits, and this gives me the certainty that this throughput model can be used throughout to any deposit. Basically, we're talking about copper, gold, iron, etc. So to summarize, basically, this compression combination is allowing for an energy efficient way of breaking particles. The piston press test allows us to predict the HPR behavior on a lab scale test. This size reduction models that were developed before allow us to get the first idea, but finally the throughput model is the final stone that gives us a complete overlook to how we can actually size completely the HPR using very low quantities of material. So thank you a lot, and I'm open to any questions.
Thank you very much, Giovanni. Sounds very promising. Cassidy does have a question. How would the implementation of technologies like HPGR open up opportunities to process hard ores that were previously uneconomic to crush or grind?
Actually, that's a very good question, because the HPGR actually allows to break the hard ores in a very efficient way. I'm talking that if we are expecting an ore to have, for example, a bond work index over 23, 25 kilowatt hours per ton, we can actually grind that material with a 50% more efficiency and in a better way. Actually, and then so we replace basically the SAG mill with the HPGR, get that energy efficiency, and then downstream, the ball mill that will grind the material for flotation will actually grind the material way easier than if the material, the rock actually came from a SAG mill. So there's a lot of benefits, energy benefits, and we can expect from a 25 to 50% energy savings using NHPR.
Yeah, thank you very much, Giovanni. Our next presenter is Kyle Powers. Kyle graduated from the University of Calgary in 2017, specializing in geology. Since 2020, he has been engaged as an exploration geologist in the Golden Triangle, delving into VMS, epithermal, and porphyry prospects. His doctoral studies at MDRU are centered on investigating how paleovolcanic architecture influences lithofacies distribution, depositional environments, and mineralization within volcanic stratigraphy in the Stewart region. Presently, he holds the position of senior geologist at Arch Cathro and Associates in the Yukon, where he is joining us from today. And he is also a poster winning promoter presenter at AME Roundup. Please welcome Kyle.
Just see if I can get this right on the first try. Which view can you see?
Oh, that looks perfect now.
Great. All right, cool. So thanks, Jonathan, for the introduction there. Yeah, so I'm going to talk a bit here very briefly about some VMS mineralization in a dynamic volcanic arc in the Stewart area. So Russell gave a good introduction of the overall architecture of the stratigraphy in the Golden Triangle. So thanks for that, Russell. There's your colloquial Golden Triangle there on the left side, if you guys don't know it. So we're kind of in the southern tip there. My study area is within that red box there on the right. So it's kind of inclusive of the old Scotty gold mine, BA, which is what I'm talking about today, the premier gold mine in there. And Red Mountain and Grand Duke are kind of just right along the flanks there. So these are my overarching doctoral questions, but I'll mostly be talking about the third one there, stratigraphic and hydrothermal controls and mineral deposition at BA, and kind of how they relate to regional lithofacies and overall structure in the Stewart camp. So these are, just for those that don't know, these are the mineral deposit or mineral occurrences within the study area here. So you have the old Scotty gold mine there in the northwest. It's an epithermal system. And then you have Premier down here, which is a vein-hosted epithermal gold system as well. And then American Creek, epithermal again, intermediate sulfidation. This one with a silver copper as opposed to gold. And then you have BA in the southeast here, which is zinc, lead, silver, VMS. So you can see here they're all. So this is the, as you would download the map from the BCGS. So a couple of the locations are a little bit incorrect, such as BA, that it's actually still hosted within the Hazelton and not within the Bowser Lake group. So that's kind of what some of the refining that I'm doing as well. So yeah, to get into, I'm going to talk a lot about depositional environments and just rocks and evidence thereof within the camp. Within Stewart, you see a very widespread dynamic environment. So you have basaltic, andesitic, and felsic volcanism, both subaerial and subaqueous. So you have, for example, there you have a subaqueous exhalative horizon at BA, and then you on the right side there, and then you also see subaqueous pillow basalts, and then elsewhere we see subaerial deposition in a subaqueous environment, which I'll get into. So I don't have time to go through all the through the maps and where all these sections are. They're all just within the Bear Pass within the Stewart area, so it's fairly proximal to the BA deposit. The first environment I'll talk about here is a shallow marine environment. We see finely bedded pumice and sand, volcanoclastic sandstones here. That's the left photo there. So deposited in a fairly quiet marine environment with a very distinctly submarine volcanic deposit sitting on top of it. We have pillows there interbedded with shallow marine limestones, and these pillows have been are obviously intruding within the limestone, so you get a bit of a breccia and a draping effect from those limestones. So that's a pretty obvious depositional environment there. And then we move further up in that section, and you're still in that same marine environment, but the energy level has drastically changed. We see a high energy reworking of those same pillows, kind of defining a fabric here, circled there in the yellow, and then you have a bit of a fabric in green. So the limestone has gone away, you still have the pillows, so you're in that same submarine environment, but the energy has cranked up. And then sitting on top of that is those fallout deposits that I mentioned. You have deposition of large blocks of pumice, kind of normally grade as you'd expect in a shallow marine environment, up from large blocks into fine bedded crystal rich tuffs on the top. So you have everything from basaltic pillows and then you go right into a nice felsic sequence here. So we've gone back into over the course of about 100 meters, you've gone from shallow marine limestones through to high energy reworking of pillows all the way into another calm environment where you're getting crystal tuffs and bedded pumice. And then we'll move just a little bit to the east here. This is just another really good example of a submarine high energy environment that's happening at the same time or just before active volcanism. So you see some reworking of this sediment here with really nicely rounded clasts in this channel deposit here, which you see immediately overlaying it. You see cross-bedded sandstones, and then immediately overlaying that again, you see those same, chemically the same, and I mean it's a couple kilometers away, but chemically the same pillows sitting on top of that deposit. So what does the chemistry tell us? As has been documented within the Hazelton, you see a evolving magma from essentially the base of the Hazelton there, sitting on top of the Stuhini group. You see basalts, you see basaltic andesites, and then they evolve over about 20 million years into rhyolites and felsic, other felsic rocks. So you can pick out those andesites. This is the distribution of the andesitic rocks on an REE plot, and then also kind of plotted up on our magma composition chart there. So you see a clear break here, separated about 20 million years into stratigraphy. So there's a fault and an anticline that actually runs right through the middle of the map there that separates the stratigraphy here. So number 2 there is the old stratigraphy, and number 1 is about 20 million years younger. And in 2, we see, interestingly enough, in 2, the older units, you see more of a continental arc affinity. So you see a more evolved magma, even though it's the basaltic and andesitic component of the area. And then in 1 there, you see a more doliitic type andesite, even though it's a younger unit, which brings us into the rift environment that we're sitting in. So at BA, we sit just outside of the SK rift. And I've plotted some rocks from 2013 or 2023 here against the work from Baresi, his PhD thesis in 2015, where he investigated kind of the entirety of the arc and the difference between the Antiox and SK affinities of the salts within the triangle. So what we see here is at BA, the question is always, whenever you're looking at the Golden Triangle, can we find the next SK Creek? And what we see here is a very clear link with the Baresi's basalt 2, which has a Antiox affinity as opposed to an SK affinity, which mineralogically makes sense. At BA, we see a very silver-rich mineralization as opposed to gold, and we don't really see much in the way of felsic rocks. So we're looking at a non-crustally contaminated back arc or similar rift environment that's sitting just off of the SK rift, as opposed to a contaminated arc that you see up in SK, where you get quite a bit of felsic rocks. So what does that all mean for mineralization? All these depositional environments. Well, at BA we see a few stacked lenses of mineralization, as you would expect in most VMS systems, but our fabrics are distinctly sub-sea floor style. So you see here on the left there, pure sea and Large's diagrams from 92 and 2014, kind of outlining the textures that you'd expect to see in a sub-sea floor replaced environment. And we see both of those. So we see the net texture here on the bottom, which sits down below in the bottom lens, which is the yellow there is zinc, and then and then you also see a bit of a massive sulfide sheet sitting above that in pink there, which is pyrite. So these textures are replacing mudstones, and because you're getting these mudstones deposited at the exact same time as all this active pillow basalts and felsic fallout and fine ash, you get a capping effect here. So you see these potting at VMSs at VA. So understanding the lithofacies here and in the region potentially will allow us to target prospective stratigraphy, both proximal to the prospect here, as well as further abroad in the Stewart Camp and potentially within the Golden Triangle. And yeah, I want to thank MTV for in-kind helicopter time and accommodation last year, and Lithos as well, because they're both involved in that project. And I'll take any questions now.
Yeah, thanks very much, Kyle. So we do have a couple of more presentations to get through. So if you do have questions, please enter them in the Q&A section, not the chat, because that way Kyle will be able to type in any answers and you'll be able to see them. Our next presenter is Derek Xu. Derek is an MSc candidate with the Mineral Deposit Research Unit at UBC. He graduated in 2022 with a BSc in geology from UBC. And prior to starting his master's project, he worked for a short time at Northwest Copper's Lorraine project in BC's North Central region. His few months of experience in the mineral exploration industry has left him eager to gain more knowledge to contribute to further exploration. Please welcome Derek.
Thanks, Jonathan. Can you see my screen and the laser point?
Yeah, we can see the screen now.
Okay, awesome. Hello, everyone. Today I'm going to talk about the host rock and alteration characterization at Lorraine porphyry deposit. So a little bit background. So Lorraine is an alkalic porphyry copper gold silver deposit about 300 kilometers away, 300 kilometers northwest of Prince George, about 150 kilometers northwest of Mount Milligan, which is here. And it's located in the Triassic-Jurassic Cornell Arc of North Central British Columbia. The surrounding area, it's surrounded by Tekla group volcanic and sedimentary rocks in green on this map. And later, it's intruded by late Triassic to mid Cretaceous Hogan batholiths, which is the gray on this map. So there are 5 complexes in Hogan batholiths. One of them called Duckling Creek Cyanide Complex hosts the Lorraine deposit. And the Duckling Creek Cyanide is about early Jurassic age. And there are so many different types of host rock at Lorraine deposit, include peroxenite, cyanide, monzonite, and monzodiorite. And at Lorraine area, there are 3 well-mineralized zones, which are Lower Main, Upper Main, and Bishop. On this map, you can see the purple is clinoperoxenite, and the pink and this kind of like a baby pink, they're cyanide. This kind of purplish pink is monzonite. So talking about the previous study, so previous study proposed that Lorraine is a kind of multi-phase intrusion area. So there's a 2-stage model proposed by previous study. So they interpret that Lorraine has the first phase, which hosts the mineralization composed of cyanide and peroxenite. And after the first phase of intrusion, the area has been tilted and then cut by the second phase peroxenite and cyanide. The second phase peroxenite and cyanide, they argue that they have exactly the same mineralogy to the first phase of peroxide and cyanide, but they're barren. So only phase 1 rocks host mineralization. And the late stage, which is the phase 3 pegmatitic cyanide dikes. So talking about the alteration, the previous study suggests that Lorraine has a kind of like a alteration zonation from potassic core characterized by pervasive K-feldspar and biotite alteration in cyanide and pervasive biotite in peroxide that controls the mineralization. And the potassic core is rimmed by late calcic sodic alteration, which is diopside, albite, magnetite in peroxide, and the pervasive or vein type in cyanide. So when I look at this rock, especially this sample from a well-mineralized zone, which is a bishop, look at this kind of cumulus texture. I have a hard time to believe this is a kind of pervasive alteration that controlled mineralization. So to understand this kind of weird deposit, because talking about porphyry, if you remember, we are talking about a porphyry deposit, but Lorraine, the major host rock, is peroxide and cyanide. Have you ever heard of peroxide as a porphyry host rock for mineralization? That's weird. So there are a few knowledge gaps. So we want to understand the mineralogy of phase 1 and phase 2, because how can you get two phases of rocks that has identical mineralogy, but one after tilting after a major tectonic event? How is that possible? So what controls on that? Are they really two phases? And then the second thing is, how can we understand these rocks, like these different rock types by geochemical data, and how can we differentiate primary minerals and the alteration minerals? So in this study, I petrographically characterized different rock types, include peroxide and cyanide, and also characterize alteration assemblages. So my samples are almost all thin sections shipped from the sponsor company Northwest Copper, cut from company selected drill holes. They're all digitized by Zeiss axial scan from MDRU, and some of them were scanned by SEM at UBC. So here, I'll quickly show you my different host rocks. So for peroxide, I divided them into two groups. One called biotite clinoperoxide. It's composed of, so the way I differentiate different host rocks is basically to evaluate the proportion of mafic and felsic minerals. So for biotite clinoperoxide, it has a lot of diopside with intercumulus biotite last K-spar. And the next one is feldspathic biotite clinoperoxide. Compared to biotite clinoperoxide, it has more intercumulus K-feldspars, and you can also see that from the thin section images. The next one is melanocratic cyanide, and so it now has more K-spar than the previous one. Same for mesocratic, even more K-feldspar. And then to the last one, leucocratic cyanide, it has just a little bit mafic minerals, mostly are K-spars. And talking about alteration mineralogy, so there are, I'm going to talk about biotite and garnet alteration. So the first one is biotite. There are a few types of or generations of biotite has been observed. So the first one is biotite 1. You can see they're relatively large. Euhedral to subhedral is found in peroxide, melanocratic cyanide, and mesocratic cyanide. Because it's intercumulus texture, we argue that it's probably magmatic origin. The second type of biotite is this kind of like a very tiny things. They usually they are very fine grained, lack of cleavages, usually grow along diopside fractures or as veins, and also formed along diopside grain boundaries. It is found like in all kinds of rock types, and it's been proposed as hydrothermal origin. This type of biotite is new. It was found from the new drilling program in 2022. They are pervasive, yellow to reddish brown pleochroic. They are associated with pervasive chalcopyrite and pyrite. It's possibly hydrothermal origin, but only observed in cyanides. And I'm going to show you like how it looks like. It's pervasive biotite with pervasive mineralization. And garnet apidol assemblages. So this one has been found from previous literature, but they argued that garnet and apidol, apidol is post mineralization alteration, and garnet is a distal post mineralization alteration. But in this study, we found that garnet is well associated with mineralization. Under XPL, garnet is an isotropic, and based on the literature, it suggests to be hydrothermal origin. And we observed that garnet usually overprint cumulus K-spire in cyanide and peroxenite. So look at the boundary between look at the contact between mineralization and garnet. It's very sharp. So we argued that garnet alteration, it's either pre-mineralization or a seam mineralization alteration. A quick summary.
We can't hear you, Derek, sorry. Yeah, it looked like we lost Derek, so probably Jonathan, if you can jump into the next and last presenter, Joanna.
Okay, yep, thank you, Virginie, and thank you, Derek, for your presentation. Our final presenter is Joanna. So Joanna, once again, is presenting on Burgundy Ridge. Please welcome Joanna.
All right, hello, thank you. Let's see if this works now. Is it working now?
Looks perfect.
All right, wonderful. That is great. All right, so yeah, my name is Joanna. I am a master's student at UBC Okanagan, and my project focuses on the characterization of the Burgundy Prospect in northwestern British Columbia, and I've done RBSR, sulfur isotopes, and trace element mapping for my project, but today I'm just going to focus on the trace element mapping portion of it. So the Burgundy Ridge prospect is a copper gold silica undersaturated alkalic porphyry prospect that is located in the Golden Triangle of British Columbia. And the reason that we're looking at this alkalic porphyry prospect is because even though they are small compared to their calc-alkaline porphyry variety, they do still host economically significant amounts of minerals. And in order to help facilitate transitions into green economies by increasing production of green technologies, we want to increase our the ore deposits that we're looking at, and these deposits tend to be not very well studied, and BC provides a unique opportunity to study them because they are quite common in British Columbia, unlike other areas of the world. So for my project, I did in situ LAICP MS trace element maps of 3 thick section samples. I picked 1 area per sample, and I did these maps to determine where metals were hosted within the deposit. So if they were associated with certain minerals or determine a sulfide paragenesis when they became incorporated into these minerals, if it was late or early. And with these areas that I was mapping, I was looking at incorporating different sulfide mineral textures. So looking at different shapes of minerals, different inclusion density, and also incorporating a few different sulfide minerals such as chalcopyrite, pyrite, and sphalerite as well. So the next 3 slides are going to have a couple of examples of these trace element maps that I obtained for the 3 samples. In general, these maps are showing the concentrations in ppm of the different metals that you're seeing. So the red is where we have the highest concentration, and then the blue is the lowest. Black is where you're not getting anything there, or very, very, very low amounts. And so for this first sample, I want to point out the occurrence of gold. So what I noticed with this sample is that gold was occurring more so around the rims of pyrite grains, and it also showed a sort of nugget-like texture, which suggests that it was probably present as micro inclusions associated with the pyrite. And also with the bismuth, it shows out of the sample, the bismuth shows these metal poor pyrite cores relative to the metal rich pyrite rims. This trend is also seen in another sample that I looked at, where again, we're getting gold mineralization around pyrite rims and also that nugget-like texture as well. And with this sample, I also looked at chalcopyrite and saw the texture of silver being incorporated into chalcopyrite crystal boundaries and along fractures. And that's probably indicative of the silver being incorporated late during the fluid evolution of the system. And then once again, with nickel and bismuth, we see these metal poor pyrite cores relative to the metal rich pyrite rims. So those trends are being reflected in this sample as well as the first. The third sample also showed these similar trends, where again, a little harder to see, but we are getting gold mineralizing along fractures within pyrite and around the edges of pyrite grains, as well as that nugget texture again. This sample, once again, is showing that incorporation of silver along chalcopyrite grain boundaries. And then again, with the bismuth, mostly with the bismuth, you see it a little bit in the arsenic, the nickel, and the cobalt, but mostly with the bismuth, we're seeing those metal poor cores, which tend to be surrounded by those metal-rich rims. Along with the qualitative analyses, I did some quantitative analyses where I plotted the concentrations of different metals from pyrite cores and rims to determine pyrite generation and relative temperature for those 3 samples. And what I saw from the nickel versus cobalt scatter plot, pyrite generation was predominantly volcanogenic and hydrothermal. We do have some sedimentary and magmatic, but it's more concentrated in the hydrothermal and volcanogenic fields. And with the cobalt, copper versus silver cobalt plot, I found that the cores plotted in a lower temperature area, whereas the rims plotted in higher temperature areas. So there was a bit of a temperature difference for the deposition of the cores and the rims. So just to kind of summarize what I found here with that. So through those trace element maps, they demonstrated that there were multiple generations of mineralization, as we saw with those metal poor cores and those metal rich rims. And the mineralization of silver and gold was incorporated late into the system, as we saw with the silver being incorporated into pyrite along the crystal boundaries and fractures, probably with fluid interactions of those chalcopyrite grains. And gold mineralization was also late, since we were seeing it along the rims of pyrite grains and fractures running through pyrite grains. Whoopsies. So what I found from the trace element maps is that late high temperature hydrothermal fluids formed the majority of mineralization at the Burgundy prospect. Some other data that I'm looking at, as I mentioned before, was RBSR geochronology and sulfur isotopes. I have an example here of a sample that I did date. And what I'm doing with that is I selected mica, so biotite in biotite veins that was present along pyrite, sphalerite, and chalcopyrite boundaries, or as inclusions, to try to get an age of mineralization from that. And with the sulfur isotopes, I will be commenting further on different conditions of the fluids in the system. And I'd just like to say thank you for listening and for coming to the talk today. And I'd also like to thank Enduro Metals, Geoscience BC, and the GSC for this awesome opportunity.
Thank you very much, Joanna. We are running over time, so I'd like to once again thank all the presenters. And if you have any further questions, certainly feel free to email them to Geoscience BC, and Geoscience BC will make sure that they get to the presenters. So thank you, everyone. And I'd like to pass it over to Gavin for his final remarks.
Excellent. Thank you, Jonathan. Fabulous presentations. I think it's fair to say our future looks very bright. So thank you to all the 2023 Scholarship Program recipients for sharing your research findings with us today. And thank you very much again, Jonathan, AME's Vice President, for moderating the Q&A discussion. Also, thank you to our webinar sponsor, Lithos Geological Inc., and to Tech Resources for sponsoring the 2023 and 2024 scholarship programs. Please do think about the value that Geoscience BC's independent public research brings to you and your organization, and how you can contribute to our future. On the screen are my contact details, and really would love to hear from you if you have any ideas and ways to support this kind of research. It's just so important to our collective future. So again, I look forward to seeing you again, either online or in person, and thank you very much and have a good day.